So I guess we're in the basement talking about data plumbing, and there's like data plumbing, I'm sure, running right there. Okay, so I'm going to be talking about Apache Kafka. I'm going to be talking about streaming platforms, and I'll be talking about a couple of new things in the Kafka universe, Kafka Streams and Kafka Connect. So how many people have heard of Kafka? Probably a good portion of people in the plumbing data basement here. Okay, good. So my plan was, okay, the down arrow doesn't go next. Okay, so my plan was to just kind of start pre-Kafka and talk about data streams and event data, then give kind of a super brief overview of Kafka because I suspect a lot of people are already a little bit familiar. Then I'll talk a little bit about how you can get streams of data into Kafka and how to process them with Kafka Streams. And I'll talk a little bit about how this kind of ties together this notion of a streaming platform. So I'm going to start with streams. And I'll try and address the question of why streaming. I guess I'll start and actually make a bold claim that you can kind of think of all your data as event streams. And some of these are kind of obvious, but let me start with an example and actually say what I mean by event. So by event, I just mean some kind of record. Maybe it has a timestamp associated with it. Maybe it has some different fields. This event is a product view, and it's in JSON, but it could be represented in any way. So now I'm going to run through a couple of examples of different types of data. And let me try and make the case that this idea of events and streams of events is particularly powerful. So the first, and maybe the most obvious, is some kind of sensor data. So this is happening out in the world where we're collecting sensors that are sending back like these kind of event records. But it's also happening in people's applications. If you have metrics or something you collect off your servers, then you're plenty familiar with sensor data. And of course, log files are naturally events. Like you can think of each line in a log file as being an event, something that happened. Maybe as a record, it's a little bit messy, but nonetheless, you can say, okay, one of these page views was an event. But maybe a little bit more interestingly, you can actually kind of think of databases as being streams of events. And this is actually a very unusual way of thinking about a database. Probably when most people think about a database, they think about a table. And probably when most people think about a table, they think about something that's kind of rectangular and has some columns and has some keys and values. So for my example, I'll try and walk through how you can think of a table as a stream. And then I'll tie this into the rest of the talk as we go on. But what I want to demonstrate here is that even things that aren't most naturally thought of in this way are actually pretty applicable when thought about as event streams. So how could you think about a table as an event stream? Well, if you think about it, a table, this is my table. I have some keys and values. But this is really just my table at some point in time. Like if I look at it, I might see this. But if I look away and look back, I might actually have some different data there. So really, a table is more like this. At each kind of point in time, I have a different value for my table. So maybe my table, at time 0 is this. At time 1, maybe it gets updated again. At time 2, it gets updated again. So really, what I have is actually a sequence of tables. And I could actually represent those sequences of tables by the sequences of updates, right? I could instead of capturing like a snapshot of the whole table at each time, I could capture just the update. And if I had this stream of updates, I could think of it as being, in some sense, the equivalent of this table as it evolved over time. And if I had this stream of updates, I could actually recreate the table. So if you gave me the stream of updates, I could make a table. And if you gave me the table, I could kind of capture this stream of updates and turn it into a stream, right? And so this mechanism for translating between a table and a stream, this is actually this kind of deep thing in data systems. People sometimes call it the table-stream duality. So I guess if you want to sound smart and feel like you learned something at the conference, you can say, well, there was a bunch of plumbing stuff, but I learned about this table-stream duality. OK, so this is my case for streams being super broad. They cover kind of natural event-like data. They cover kind of messages between applications. And they cover also like stateful things like databases. So what are they useful for? Well, there's really kind of two uses for these streams of data. One is building data pipelines, which I guess is our subject for today. And the other is being able to kind of tap into these pipelines and be able to transform the streams or process them or react to them in some way. So you can build something kind of like a service that taps into this and does processing. And I'll talk about this type of stream processing in this talk. So how does this actually work in companies? How do companies actually perform these functions? Well, in practice, I think it's often kind of a giant mess. Like you have kind of ad hoc data pipelines between things. You have kind of point-to-point communication. You have basically a bunch of things that are kind of shoved into a batch processing context or some kind of request response context, even though in the business they're actually asynchronous. And so I'll talk a little bit about how this idea of data streams can kind of clean up this picture. And the first thing to get your mind kind of into this mode of thinking is when somebody says data pipeline, think of an event stream. So all those arrows on that big messy picture before, you could think of those as being some kind of ad hoc event stream, maybe just a poorly specified one. And the key idea behind Kafka, and the idea I'm going to dive into, is that you could have some kind of central platform for these streams. You could collect them in one place. They could all work the same way. They could be represented the same. And this could connect both data systems, where you're maybe connecting to capture streams of data or connecting to load streams of data. But it could also connect like applications that react to the streams or publish messages into it. And it could also connect analytical systems that do monitoring and so on. And there's some benefit to this type of streaming platform, this type of event-centric thinking. So I'll walk through an example. Maybe I have a web application, and I want to capture my product views using the example I just gave. And I want to get those into Hadoop for analytics. So I could publish them into this streaming platform I just talked about, and I could load them into Hadoop. And in this model, it's not really clear what the benefit is. But over time, as I have more ways of capturing product views, right, the nice thing is the Hadoop system doesn't really have to know about it, right? So I have some kind of pub-sub model where Hadoop knows it's interested in product views. These things, they make them, but they don't really know about Hadoop, and they're kind of decoupled. And if more things end up using the data, then they can do that without having to connect to these things as well. So instead of everything kind of connecting to everything else, you can say, well, I subscribe to the product views. I know what I do with them. I do something for the business. These things say, OK, I know I produce product views, but not everybody has to know about each other. So this isn't anything really new. It's just kind of like pub-sub messaging. But if you can do it at the kind of scale that you would need to really run a whole company around, it becomes kind of a different model for treating data. And this is kind of this streaming platform idea, that you could capture all these streams, that you could have them available to everything else, without everything that creates streams of data having to know about everything else. So that's kind of my introduction to event streams. Now I'm going to dive into Apache Kafka. Kafka is a system that was kind of motivated by that worldview. And it is kind of at heart meant to be the thing in the center there, the thing that collects all the streams that kind of multiplexes them. And it is kind of a cross between a pub-sub system, like a messaging system, and maybe something like a file system. So it's a little bit different from a traditional messaging system. It actually stores a persistent log of what happened. So the fundamental abstraction in Kafka is this type of log, and it's basically a sequence of events. It's a sequence of records. And each of these records is given some number. And this type of log, it's more akin to like a commit log than like an Apache log. And it's readable, so it has an API to subscribe to it, and it's writable. But when you write, you just append. And these events are all immutable. So it is a system that's built around directly modeling this idea of events and making them something that can fan out and be subscribed by lots of processes. And this turns out to be a pretty good implementation of scalable publish-subscribe messaging. And this is basically Kafka's data model. It's a Kafka topic, which is like a feed of data, maybe all of those product views in the example I gave. It's basically just a partitioned set of logs. And writes are going to be multiplexed over these logs. And reads are going to be off of this set of logs. And this handles even this notion of replicating changes. So a really common thing to do with Kafka is to publish database updates. Right? So as updates come into some database, it's publishing them into this log, and then other replica systems can take those. And so the replicas could be other databases, or they could be search systems, they could be applications, and we'll get into that. But in this case, the record that's being captured is the kind of key value pairs. This is the key of what was updated. This is the new value for that update. And I'm going to talk more about this type of change log as I get into it. And the final bit of Kafka is allowing you to have groups of processes that consume these streams. So Kafka has a notion of consumer groups. And this is a set of processes. So the A's in this picture are a consumer group of processes, and the B's are a consumer group of processes. And you can have this group subscribe to some feed. And this allows the processing to scale beyond the capabilities of one process. And it allows these groups to be fault tolerant. So if one of the A's dies, the remaining A's take over its work in processing. If a new A comes along and joins the group, it'll take over some of the work. And so those right there are basically the core abstractions in the Kafka cluster. And the trick of what Kafka does is just try and implement this as a full-fledged distributed system with fault tolerance and a strong consistency model and security and all the things you would kind of expect of a modern data system. And Kafka is open source and widely used at a variety of companies in different industries. So this is kind of what we were aiming for, was to make it something that could work at this kind of company scale in this type of streaming platform. And now I'll dive into two related pieces of technology that are part of the Apache Kafka project. One is Kafka Connect, and the next is Kafka Streams. So Kafka Connect is all about these arrows. So I drew these kind of nice lines, which makes it look like it's very easy to get data in and out of Kafka. But what Kafka Connect is actually our attempt to make that really easy to do. So when we built Kafka, we built it obviously with APIs. There's clients in different languages. But fundamentally, if you're integrating MySQL to capture changes into Kafka, you're probably not the only person in the world doing that. And it turns out that there's actually a lot of shared problems between these types of connectors. And what we wanted to do was build a framework called Connect that would allow you to build this type of streaming pipeline and take over as much of the hard part of the problem as possible. And so this could be either a connector which is attaching to some data source and streaming changes into Kafka, or it could be on the other side. It could be streaming changes out of Kafka into some kind of data sync, right? So I'm going to use this sync and source terminology. And the key thing that this framework does is it does kind of the hard work of building this type of streaming pipeline. So it makes it possible to scale out these connectors. So as a connector implementer, you just basically tell the logic for how to read or how to write rows to a particular system. And Kafka Connect will handle how this scales out across multiple processes, how those processes are fault tolerant to make sure that you're always consuming from the system, how you manage these processes if you have lots of different data sources and data syncs. And then also, and this is probably one of the deeper parts of the problem, how you propagate whatever schema information you have or don't have about your data sources. So if you're capturing data from a relational database, you probably have a great deal of structured information about what your data looks like, all the types for all the columns, all the names for the columns. If you're capturing data from kind of a key value store, maybe you have less. Maybe you just have some byte array schema. But nonetheless, you don't want to lose that information for all the downstream people. And so fundamentally, what this is about is, being a framework, you can build these types of reusable sources and syncs and deploy them. And you can, so some of the examples that we have a Hadoop sync, and this kind of demonstrates how you can take something which is scalable like Kafka and something which is scalable like HDFS, and you can run this connector and scale it out over multiple processes so the pipeline itself is, scalable. And of course, if one of these processes dies, the work will be taken over by the remaining ones, and you can dynamically scale the pipeline. But you can also do this for something like a JDBC database. So in this case, it's just probably a single server relational database. And so you might wonder, well, why do you want to have this ability to kind of scale out over processes? But what we found is most people don't just have one relational database. They usually have a number of them. And if you want to actually kind of cover all of these in a way that's operationally efficient, you don't want to be spinning up new processes per database. And you would have to have at least a pair for fault tolerance. So this is a way you can kind of set up this Kafka Connect cluster. You can dynamically, via the REST API, add these database sources, and it will stream data from the database into Kafka. And we've collected, I think, a few dozen now of these different connectors out in open source or ones that the community have built or whatever. And so you can actually connect a pretty large set of things to Kafka in this kind of off-the-shelf way without having to actually write any code. So that's Kafka Connect. Now I'm going to dive into the next new feature, Kafka Streams. So Kafka Connect was released in the 0.9 release of Kafka. That came out at the end of last year. And we've been building out that connector ecosystem since then. The 0.10 release is basically about to come out. So it's being voted on right now. It should be the final release probably by early next week. And one of the major features in that release is Kafka Streams. So if Connect is how you capture streams of data, Streams is basically how you process it, how you build applications that react to these streams, transform them, process them. And we had kind of a lot of experience working with this type of stream processing framework. The team that came out of LinkedIn had built Samza. And we really had a very particular thing in mind we kind of got out of our experiences when we were designing Kafka Streams. And I'll kind of walk through it. But I want to kind of start just maybe from first principles and ask the question, what is stream processing? And I'll try and answer that question. I'll lead into how I think that motivates our solution. So the reason I ask it is because people tend to have a lot of misconceptions in this area. They tend to think it's an area that needs to be very complicated, that tends to be kind of transient and approximate and lotsy. So it's fast, but it's kind of getting the wrong answer. And I actually don't think that's true. I think stream processing is basically really just a kind of third paradigm for programming. Like one way to split up programs would be how they get their input and how they produce output. So most people are probably familiar with request-response programs, which is like a web server or web service. That's a request-response process. And most people are probably also familiar with batch processing. Probably if you had a computer science degree, the first program you wrote was some Unix utility that took in data and processed it and spit it out. And so these batch processes, this might kick off kind of throughout the day. And stream processing is going to be kind of our hero, and I'll contrast it with these. And rather than thinking about this as being kind of a limited form of one of these two, I'm going to actually kind of argue it's a generalization. It's actually something that can do a lot of what request-response processors do and a lot of what batch processors do. And here's how. So when you think about request-response processing, you're kind of giving one input, which is the request, and you're getting back one output, which is the response. And when you build something like this, you kind of run it, and it processes, in some sense, the stream of future requests that come in. It doesn't, if you write a web service, it doesn't go back and process old requests that might have happened in the past, obviously, right? So this is about, one input, one output, future requests. Batch processing is kind of the opposite. In a batch process, you get all your inputs up front, you kind of churn through them, and then you produce all your outputs all at once. And inherently, when you're running a batch process, it's about all the requests or the inputs which have already happened. So it's about processing past data. And stream processing, in my definition, is just going to be kind of generalizing those two things. So instead of saying, well, I'll take all my input up front and I won't give any output until I get all my input, I'll say, no, I'll let the program pick as much input as it wants. So it can choose how quickly it produces output. And it can choose how much output it gives. So it could choose to just take one input and produce one output, in which case it's kind of like a weird request-response processor. And it could choose that it kind of takes all its input, produces all its output, and then goes to sleep until tomorrow, in which case it's kind of like a batch processor. But most usefully, it can actually do anything in between, which, and I think this is the most critical part, it actually lets you kind of control the frequency of processing and the latency that the output gets, which actually dramatically, I think makes a lot more simple these kind of data-intensive batch processes if you can kind of make them much more real-time and integrate them back into the user experience, into the customer experience. But the second part of this is it generalizes this idea of processing the past and processing the future. So if the batch process was all about past inputs, which had been already written down and recorded, and the request-response processor was all about future inputs, this allows you to kind of process from the past and just keep processing into the future. So it's kind of as if you had a query and it was able to process the data in the table, but just keep updating as the table itself was updated. And another way to think about this is, look, you can think of a stream processor as just being a kind of microservice, which is event-driven, has access to this past data, and has kind of stronger semantics than maybe a REST service would. So this is kind of my view of stream processing. I'm particularly interested in it because I think a lot of the stuff that happens in a business can actually be thought of as data streams. So if you think about like a retail example, since most people understand retail, you can think about there being kind of a stream of sales that are occurring. You can think about there being a stream of shipments of products from distribution centers to stores. And then in response to this, you can think about the stream processor recording inventory adjustments or making price adjustments. And you can think about it producing output streams such as what products to reorder or detecting fraud or doing analytics off of this. And so you can think about even kind of common business processes that we're super used to as being these types of stream processors. And so there's a couple ways you can implement something like this. There's a couple ways you can build stream processing. One is just build an application and use the kind of Kafka APIs, right? And you could consume a stream of data and you could produce back maybe some derived stream. And this works pretty well. It's actually pretty simple, but there are some hard parts to stream processing. How do you partition this out? What are the fault tolerance semantics? How do you do stateful processing like joins and aggregates? And how do you reprocess stuff if your code changes? And this is kind of where people turn to stream processing frameworks like Storm or Spark Streaming, or the one that we had built was called Samza or Flink. And these are all these different ways that you can kind of have some clustered processing that helps you write an application that processes streams. And we built one of these. We built Samza and deployed it actually relatively widely at LinkedIn. And what we found was people were kind of trying to build something like a microservice, but the way we built it was kind of a lot more like a MapReduce thing. You deploy your app into this cluster. It tries to kind of take over and manage your app. And so although that worked relatively well for kind of analytical jobs, it didn't work that well for these types of core applications that were kind of part of the business. So we've started from the other side of the problem to make Kafka Streams. So what it is it's not really a stream processing framework. You don't set up like a Kafka Streams cluster. It just works with your existing Kafka cluster. It's just a simple client library. We've done a Java version of it so far, although we'll extend it to other languages. It gives you a convenient DSL. It gives you kind of the state-of-the-art in stream processing features. So it gives you advanced windowing and reprocessing, and it doesn't batch data, so it works with low latency and allows you to do kind of stateful processes like aggregations and joins. But I think the critical thing here is, it's basically just built around the Kafka APIs. And so it doesn't require any cluster of its own. It can basically fit into any existing application that you have. And what we were aiming for here was to really take this area of stream processing and make it as simple as possible. Make it something where you could get kind of the capabilities and features you would expect out of a stream processor, but without the heavyweight commitment to something that's going to own how your code is deployed and how it's configured and how it's monitored, something that you could just deploy in any fashion you wanted. And that's what we've done. So a Kafka Streams program looks something like this. If you're used to the Scala collections library or the Java Streams API, it's very similar to that, except it just includes a little bit about the semantics of streams and serialization and offsets and so on. But this is the transformation. So you can kind of very concisely specify something that does, in this case, word counting, I think because you're required to count words in any big data example. But you can kind of very concisely specify how to do that. And this will basically transform from input Kafka topics to output Kafka topics, even doing kind of stateful aggregations with updates that come late. And the way that this executes is you would embed the Kafka Streams app into your application. It subscribes as a Kafka consumer, and it produces back derived streams. It takes that kind of processing that you've specified, and it divides it up over instances. You can dynamically add new instances to the processing, and those will take over some of the work. And if they fail, of course, that work goes back. So what Kafka Streams is doing is all of this about dividing up work, managing state, giving you this kind of higher level API. What it's not doing is any of the how do you deploy your application. So we're assuming you have some way to deploy your application. And the result is this kind of works with the whole spectrum of deployment things, from the kind of very uncool but very well understood rsync to the very cool but you may hurt yourself distributed deployment frameworks. And obviously, if you're running in something like Mesos or Kubernetes, you can kind of elastically scale out your process. And it gives you kind of the key operations you would expect. You can kind of take a stream and transform it. You can filter items. You can aggregate, meaning like count or sum or whatever. And you can join streams together. And then most importantly, it extends this not just to streams, but also to tables as well. So I talked about that notion that you could think of a table as a stream of changes, a kind of change log. And what Kafka Streams is going to let you do is actually process those change logs. So in this example of retail I gave, where I am keeping track of inventory or price adjustments, that's probably effectively a derived table off of these streams. And Kafka Streams naturally supports that. So in this changelog picture, I talked about how you could use Kafka with a kind of log of updates to replicate data to other data systems. But most importantly, with Kafka Streams, you can now take that stream and not just replicate it as it is, but transform it into some kind of like materialized view, some kind of new view of what the data looks like, and have that be the thing that other systems or applications subscribe to. And each of these operations, the kind of aggregations and joins, they work with both streams and tables. So you can take something which is a change log, and you can compute an aggregation on it, kind of a materialized view. You can take something which is a stream, like the product views, and you can do the same. And you can join them. So you can have a stream of product views. You could join on table information about the products or about the viewer. And this, I think, is a key thing that is not that modeled that well in existing stream processing systems. And this works well with Kafka Connect. You can have connectors that run in Kafka Connect. You can do transformations in Kafka Streams and get data back out with Connect. So you can think of it as kind of being, Connect is kind of the E and the L in a kind of streaming ETL, and Streams is the T. But of course, you could substitute other things here, like you can have your application directly write to Kafka. You don't have to use Connect. Or you could use a different stream processing system or just a plain application to do the transformation. OK, so those were kind of the two new features that I was interested in introducing. Kafka Streams will have its first kind of full release in the next week. And I'll talk a little bit about how these come together. So a few of us had the opportunity of actually doing this at large scale at LinkedIn, where Kafka acted as kind of this streaming backbone for all these different types of data and supported kind of a whole ecosystem of real-time things. And this is something that's been done over and over again at different companies. So when I showed that open source slide, a lot of companies have these really big kind of Kafka-based data pipelines or data backbones. And those of us who worked on this really learned a lot out of how to build this type of streaming pipeline, what's required to operate it, how it integrates into things. And so the company that I founded after leaving LinkedIn is Confluent. And we've been building out kind of an open source platform around Kafka that helps you put some of these things together. So the Confluent platform is open source. We're including clients for Kafka. We're including a lot of the connectors for different systems, so people can get those off the shelf and have them tested all together. We're including management and monitoring tools, REST access, and a lot of kind of schema maintenance tools. So kind of the full set of things that we felt companies were building in-house. We're trying to produce some high-quality open source version of these that people can run against. And that's it. So if you're interested in this stuff, there's more detailed blogs on both Connect and Streams, so you can kind of dive in and learn more about them. I realize these are kind of long URLs, so maybe just Google. And I think I have a few minutes left, so I'll take a few questions if there are any. And then I'll hand this over to whatever's next.
Please come up with the questions to the mic. That's OK. I'll carry the mic.
Just a very quick question. What versions is Streams going to be compatible with, or only the newest?
Yeah, so the question is, what version of Kafka will Streams be compatible with? It does require the newest version of Kafka, which is 0.10, The reason for that is 0.10 actually adds a timestamp field to the Kafka messages, and that's actually very important for these windowing features to be done correctly, so that you can handle late data and aggregate correctly and so on. And so theoretically, it would be possible to make it work with older versions, but it's a bit of a hack, and you have to kind of do everything twice.
Hi. Does Kafka Stream does almost all the transformation that is done by a regular ETL tool like Informatica or any other?
Yeah, that's a good question. So Kafka Streams right now is kind of a developer platform, meaning you have that kind of lightweight Java API. In that sense, yeah, it does do everything that something like Informatica does, but Informatica actually gives you a really nice UI. If you're interested in that, one of the tools Confluent is going to be putting together is something which helps a little bit with that kind of streaming pipeline. Other questions?
Yeah. How does Kafka Connect deal with like schema migration, data migration? What happens if the data source changes?
Yeah, that's a great question. So Kafka Connect doesn't itself do anything other than propagate the schemas. But that schema registry that I kind of listed as one of the open source things Confluent produces does do that. So very often you want to have it be the case that you don't just blindly propagate schema information. You also enforce some kind of compatibility so that people can't publish invalid messages or something like that. That schema registry I kind of pointed to helps with that kind of thing. So you can, for some topics, say, well, it's a free-for-all, do whatever you want. And for other topics, you can say, no, look, I want this to be backwards and forwards compatible, so I'm only going to allow data into this topic if it has the right fields and so on. I'll allow changes, but they have to be compatible changes. In either case, Connect just allows the schema to propagate. So if I talk about that like HDFS connector, that makes it possible to have a Kafka topic and have updates and new fields kind of percolate downstream all the way to Hadoop, so the Hive table gets updated automatically, and you don't have people trying to maintain that by hand. That's probably a very short answer to a long question.
Simple question from enterprise side. The Kafka is not matured because it has a 0 dot something version number and not 1 point something. Do you know why is that? And it's there. I know it's pretty reliable and consistent. Mm-hmm. Do you know why it did not get promoted to 1 dot something?
Oh yeah, I mean the version numbers are just kind of an open source thing. So our take was we wanted to get finalized client APIs, security, connect, and streams in. So probably in the next release we'll do that. But I don't think it really reflects on the kind of robustness of the software. It's used at pretty large scale at a pretty large number of companies. Usually for that to happen, it has to work. Otherwise the companies dump it, right? So I wouldn't read too much into the version number. All right, last question, and I'm happy to take anything else offline.
Thanks. It seems that doing stateful programming with something like this is particularly tricky, especially if you're basically have a consumer group and one machine picks off a piece of information that's needed to compute state, and then another machine picks off another piece of information needed to compute state. They each don't have enough to compute the proper state and then write it to another stream. Do you guys have bits and pieces of software that more or less automatically handle that, or is the programmer basically still stuck being careful, making sure that all the machines have enough data to do the right state calculation?
Yeah, that's exactly one of the problems Kafka Streams tries to help with. So I think, as you say, if you were just blindly subscribing, you could imagine trying to partition things in some way that would have the right things end up in the right way, but you'd have to be very careful. Kafka Streams, I think, makes that significantly easier in that it knows about the partitioning model and kind of enforces that. It knows about the state model. And so what it's doing is it's basically allowing this combination of partitioning and local state to kind of do what you would expect, right? So if you have a join, the things that are being joined have to be partitioned on the same key so that they end up in the same place so they can be joined together locally and vice versa. So yeah, I think that's actually, I guess, the value add that something like this has is it helps manage the state, helps make it fault tolerant if the processes fail, helps make the failover very fast, and then it kind of isolates you, the programmer, from having to think in kind of as low level detail about how your data is partitioned at each phase and so on. Cool. All right, I'm happy to take any other questions offline. Thank you all.